This is the only thing. Things.
And we're good. And you're good up to that dotted line right there.
So problem 5 will be take home or bring from home. Right? Available. And it's given. One of the problems will be available, let's say, sometime this week or surely by next Monday. Right. So you have 2 weeks from now, right, for the exam. So it will be surely available, hopefully, as soon as I just have to type it. It's on the content we are studying now. It will be long, but at the same time, it will be exactly like a homework. It will be guided. So each step will be simple, but overall, it might be a tedious, Anything you guys have to point out? You want to mention about the exam or general how things are going?
You think it's gonna be about the same amount of problems as the first one, like 6?
Yeah, there'll be 5 problems. So one is already available. So 4 problems in about 75 minutes. So time should not be a constraint. Was it a constraint last time? The time?
Not really.
So
But this time the some homework problem is solar. So
yes. So I won't. So it will be part of the homework problem. So actually that leads me to comment. So for example, the current homework, all the problems that you have to submit, they are reasonably small. And it is easy to survive the whole of your physics career without going through the detailed problems in the early part. But if you do not work on those problems, you might find difficulty in manipulating these functions. We're doing Legendre polynomials. You might have difficulties in manipulating these polynomials. So it's like saying double angle formula in trigonometry. If you never derive them, you can survive the whole of your career without that. There are identities, they treat them as identities and you will be able to manage. But if you have to do something from the scratch, then these ideas help you a lot to manipulate these functions. So in that, it's the same spirit. We are introducing Legendre polynomials. You can manage just by knowing the identities that are associated with it. And if you have a reasonable idea of what they are meant to be, you'll be able to manage. But if you have the details of how these are manipulated, you will have a lot more control on them when you're building things. So I'll go through some of them in today's lecture, and on Friday's lecture, you will get a feel for how you manipulate them. But we go through the problems. I have not made it for submission. They are only for understanding purposes, but go through them if you can. Yeah. Okay. So to answer your question, they are all long. I can pick something small out of it, like the manipulation part might be straightforward, but if you have once seen it, it is straightforward. If you have not seen it, it might be non-trivial. So in that sense, at least go over it. Don't just ignore the whole. No. Oh yeah, I was missing you. So how did I not count you? Yes. Was your trip? Oh, yeah. Take your breath. Okay. So we introduced Legendre polynomials last time. Half of us were not available or not present in the class. So I will very quickly go over it. And even though we introduced the Legendre polynomials, we only got to the P1, I think.
Yeah.
So we will just get to higher orders. And then we want to see a pattern in them. And we will derive that pattern also. It's convenient, but not really necessary to have that pattern. Once you know the definition of Legendre polynomial, that is all that is needed. This is Legendre. And this is these polynomials are motivated from the idea of the electric potential due to a single point charge, which is 1 over r. But of course, electric potentials were not there in 1800 and so on or earlier. So it is more motivated from the gravitational potential due to a point mass. So the idea is 1 over r is the potential, and this is when the charge is at the origin. If the charge is not at the origin, then you write this as 1 over r minus r prime. Is that clear what I mean from here to there? If I set r prime at the origin, that is the charge at the origin, then this reduces to this. So it is 1 over r most of the time when we study in the introductory physics courses, but you have choice to keep the charge or the mass at the origin once. If you're dealing with 3 charges, then you don't have the choice. So you have to deal with non-origin points. And this we said is equal to 1 over r square plus r prime square minus 2 r prime times the angle between these two vectors. And we said this is cosine gamma. That's here, where r dotted with r prime is equal to r prime times cosine gamma. So this gamma is the angle between these two vectors. You immediately see a structure. Let me write that also. That could be r and r prime could be maximum. One of them you have to pull out. So we introduce a definition of maximum, or we use the word larger, I suppose. Maximum of r and r prime larger, I guess that is a better word. Larger among the two. So whichever is larger will be called r greater, and minimum of r and r prime, we'll call it r less. Pull out the r larger, and what we get is 1 plus r less over r greater square minus 2 times r less over r greater times cosine gamma. We introduce the idea that P is equal to r less over r greater and x is equal to cosine gamma. And you immediately see that this can be written as, so we introduce the idea that GTX is equal to 1 over 1 plus e squared minus 2 times t times x. I started from here. If you're keen on physical interpretation of what is going on, but as far as mathematics goes, you only need this function. This function is square root of 1 plus t squared minus 2xt, but what is the origin of it? That is coming from the point charge electric potential or gravitational potential. And if you're studying planetary motion, you're interested in making this as precise as possible. And that's why you want to analyze that. So that was the motivation, at least historically speaking. But you can start from this point and you don't need any of this. That's just to give a physical insight of what's the context in this. Expand this as a series in T. Okay, L equal to 0 to infinity and T raised to L. If you write that as a series in T raised to L, it will have coefficients in front. These coefficients are called the Legendre polynomials of order L. That's the definition, if you want. So this is the generating function. Of Legendre polynomials. Wasn't there a quiz? Okay.
Yeah.
So yeah, maybe I should have the practice of collecting them. Right? Obvious. Perfect.
I said I'm late, that's why I didn't submit in the last.
Oh, yeah.
Yeah.
Yeah, because we didn't start this practice yet, right? But thank you. Since this is the first time we are collecting, if you're not submitted now, submit it in my mailbox, but from the future, no, right? So a couple of, let's say, until Friday, I will accept it on mailboxes also, but after that. And it's just because it is too much botheration. I mean, if I start managing it on the mailbox and here, it's too much work on my. Okay, so going back, sorry. We have a function which is dependent on two variables. It is called the generating function of Legendre polynomials. And you expand it as a series. Anything, any function is has a unique series associated with it, and the series, in terms of an expansion in T, the coefficients of them are called the Legendre polynomials. Now, the first time when you really define it, it is tedious. You have to do this manually. If you have ever tried to sine and cosine functions, 2000 years back, someone did it manually and it was known only to one significant digit. Imagine sine of 45, you know it only to one significant digit. So it's that is how astronomy was done. And since astronomy was so successful, they started doing this better and better. But one of the limitations, at least, was knowing trigonometric functions to high significant digits. Same idea here. Prediction of planetary motion was very successful after Newton, so they wanted to do it better and better. So you wanted it higher and higher. Last time we did this for L equal to 0 and 1. So we will do it for L equal to 2 until 2 here in a very crude manner. But then we will see a pattern in there, or we will try to see a pattern in the whole thing. And then it will become easier to discuss. So that's the definition in principle. And let's try to get that definition at least for L equal to 0, 1, 2, 3. So here L is 0, 1, 2, 3, and so on. And it's also good to, if you're physically motivated, this L that you see here is pretty much the same as the, what is it called? Magnetic, no, it's not called the magnetic, angular quantum number in hydrogen atom that you see. There is an NLM hydrogen atom states, energy states of an hydrogen atom are labeled using NLM. That's the same L here, angular momentum. It is associated with angular momentum L and same L, but here the motivation is entirely different. It just seems like it is a label for a series expansion, but it will get connected with the angular momentum once we include the spherical symmetry. At this point, it is only one angle that is coming in. So X here, because it is related to cosine gamma, it is less than or equal to +1 and greater than or equal to -1. And T here is R less over R greater. So that can never be negative. So T is greater than or equal to 0 and less than infinity. Again, this is how you begin, exactly like sine function. You begin by saying it is spanning an angle between 0 to 2 pi, but they can be extended to imaginary quantities. So sine function is defined for any complex number. So that's called analytic continuation. So similarly, you begin the first introduction to Legendre polynomial is done within this range of the variables. Gamma is 0 to pi. So gamma is 0 to pi. But these two are related. Okay, so how do we get this? Just expand this quantity. Remember 1 over 1 plus x. Right? Square root is 1 plus x raised to half, and that's equal to 1. No, minus, right? So minus half, 1 plus minus half times minus half minus 1. No. So I start with the power minus half and then x and divide it by 1 factorial, and then you do minus half times minus half minus 1 divided by 2 factorial times x squared, and so on. Keep subtracting them and you keep going. While we are here, it is also good to see a pattern. Can we write this as a sum? Yes, of course. So let's write this as, how do I write this? Help me. It starts from -1/2 and it will go raised to n. So you say this is say m equal to 0 to infinity, and x raised to m is surely there, and m factorial. And how does this power go? There's a -1 raised to m, right? And in the denominator, there's 2 raised to 1, 2 raised to 2, 2 raised to 3. So probably there is a 2 raised to m in the denominator. And here it starts from 1 and a 3. So it goes from 1, 2 plus 1, 3, right? 1 times 3 times 5 times, how far does it go? So it is 2m plus 1, is that correct? So 2m plus 1. Notice this goes from 1 and 3. Next one will be 1, 3, 5, 1, 3, 5, 7, and so on. So it goes to 2m plus 1. That can be written as m equal to 0 to infinity x raised to m
m factorial minus 1 raised to m. And that's let me also write 2m, and this is 2m plus 1 factorial. But then I have provided 2, 4, 6, all the even powers I have provided. So that's equivalent to saying 2, 4, 6, and so on until 2m. That's the same as I pull out a 2 raised to m, and then there is m factorial. So I think this is 2 m factorial times 2 raised to m. So 2 raised to m can be collected, m factorial multiplies, and that's equal to. So this is m equal to 0, infinity x raised to m minus 1 raised to m, and you have 2m plus 1 factorial divided by m factorial square and 2 raised to 2m. Okay. That's just a pattern in this, but what I'm going to first do is, of course, we would like to get PL in a complete sense using this, but let's well, I think we last time did it for in that form, so this time let's do it this way. So this is equal to GTX, the generating function then is equal to, and that's equal to m equal to 0 to infinity x raised to m, but x is now p squared. The whole. I think I used a bad notation. This x has nothing to do with it. This x. This is a random variable. I picked 1 over 1 plus x. Typically, you write a variable. So this x has nothing to do with this x. So don't confuse. So here x is not equal to cosine that. That's just right. We're waiting. So that's so here there is an x there. That's a confusion that can come in, and that's minus 1 raised to m. And you have 2m plus 1 factorial divided by m factorial plus 2. I can as well put this inside minus what can be pulled in, and let me do that. So this is 2tx minus t squared raised to m. But this doesn't immediately allow me to collect my PL because this is not on the form t raised to L notation. So I have to still expand each one of them and collect t's. So we will do that manipulation of sums in a few minutes, but let me at least by brute force try to calculate m equal to 0 and so on. So let's say t or m L equal to 0, right? So L equal to 0 will be the power of t raised to 0. All the coefficients that are t raised to 0. When m is equal to 0, this whole thing is 1. That is surely the case. When m is equal to 1, at least there is 1 t. So that doesn't contribute. So it is just m equal to 0 that shows up. So we immediately know that p0 of x is equal to m is equal to 0. So it is is 1 factorial over 0 factorial square times 2 raised to 0, so that's equal to 1. So we learned immediately that P0x is 1. We did this last time also, but we literally expanded it in the root book. So that's the same thing we are doing here. So power of t raised to 1, so that's, I'll go only till t raised to 2 and then come back and manipulate this sum. What is the power of t in this? So m equal to 0 I have taken care of. M equal to 1 has a power of t in here, and that is the only thing that will come in when m is equal to 2. It will start with t square at least, so there will be no power of t. So power of t will give you p1x would be equal to contribution from m equal to 1, so it is 2 times 1 plus 1 factorial divided by 1 factorial square and 2 raised to 2 times 1. So that's 3 factorial plus how much? 4. No, 3 to 6 divided by 4, 3 by 2. 3 by 2. But then whenever m was equal to 1, the power that we had for t here, okay, so that is an x in here, right? So that is 2 times x. Am I missing something?
No.
I think I'm missing something. How?
So P is 1 over here.
Because that is not P1x. I think to my understanding, P1x is
This, yeah, it's just it's.
it's just x, right? So what did we miss? Okay. So m I'm setting it.
I think over here in inside the bracket 2tx minus t squared.
Uh-huh.
I think we missed something from the not in the last part.
Oh, here.
Yeah.
So 2, right? That's the 2 that way.
But there will be 3 by 5.
Okay, let me try again. Sorry. Okay. So we're getting power of t, right? So that is 2 raised to x. So P1 of x will be equal. If surely there is a 2x, correct? And I have to set m equal to 3. Yeah, I'm just going to write it explicitly. 2 raised to 2m square. Set m equal to 1, right? So that's equal to 2 times x. 2 times 1, 3 factorial. 2 plus 1, 3 factorial.
3 by 4.
1 factorial is gone, so this is 4.
It will be 3x.
Right?
It will be 2m minus 2.
Here, this one?
Yeah.
Oh, so let's see. Okay, good.
Because if we set m as 2, then m as 1, and that becomes
MS1, oh, so this becomes 3. So we are going one farther. Good. Thank you. Thank you. Thank you. So I'll correct this. So this is 2m minus 1 instead of erasing it. I'm correcting the squared brackets are getting corrected. So this is 2m minus 1. Thank you. Thank you. So this is 2m minus 1 factorial. This is 2m minus 1 factorial. And did we get this correct then? The denominators? Because if it is 2m minus 1 factorial, so then we go 1, 3, 5, and 2m minus 1. Oh, so we do, when we put in the 2, so that is 2, 4, 6, we introduce the 2m also, then everything else works in. So we provide that 2m also the extra at the very end, that is also provided. So these two remain the same. Thank you. Yeah, so that's good catch. So hopefully now it works. So let's see. So this is -1. Try this again. So m is equal to 1, so 2, so that's 1 factorial. And this is 1 factorial square. And that's 4.
That comes to 1 by 2.
Hmm?
That comes to 1 by 2.
And is that correct?
Yeah, you 2x times 1/2 of that.
Is it 1 by 2x?
Oh, you have the 2x. Okay, wait,
No, what is P1x?
it's just half.
Just x, right? Okay, so let's go back here. Okay, let's check this. We should have got 1 here, right? So when m is equal to 1, that's goes away. So this gives you a 4, right? Okay, let's do this properly better. Okay. So it's clear that this goes to 1, 3, 5, and this goes all the way to 2m minus 1. Agreed? That's for sure. And did I do this division unnecessarily? No, there is a 2. This is 2 squared, so this is 2 raised to 1, 2 squared. I think that's correct. And now multiply and divide, correct? So this is m equal to 0 to infinity x raised to m factorial minus 1. So I'm providing 2, 4, 6, so on. So this is 2m factorial, let's say. But that's not the same as above, so I have provided extra. So first of all, I have provided, so what is the extra things I have provided? 2, 4, and so on until 2m. Pull out 2 raised to m, and I have m factorial, right? So this is 1 over 2 raised to m factorial, which is what we had earlier. Does this work? When m is equal to
So 2 by 4, I think that works now. We'll get the x for that.
because earlier I wrote 2m minus 1, correct? Now I'm
Yeah.
writing 2m.
If we go with the 2n, then we will get the x.
Am I good? We'll see. At least 2 of them has to work, right? So they get stuck again. Or let me check my notes. Let me look. In my camera. Yeah, this seems okay. And there is a -1. Edited from minus. Okay, so this seems correct. So this will be. So this is 2m factorial. Sorry about the confusions. And this works out well, I guess. Okay, here. Over. So this is 2m factorial divided by m factorial squared. Well, that's equal to 2 times x. M is equal to 1, so that's 2 divided by that's 1 and that's 4, so that's equal to x. Okay. Better. Clear? Any questions? Sorry about the confusions. Let's do t equal to 2 also, just to show how complicated this gets very quickly, because you have to collect all the t's, right? There is a t. If you are doing t square, there is one part that is in m equal to 1, and there is one part in m equal to 2. So power of t square will be equal to, so this is p2x, and you realize that where is it coming from? When m is equal to 1, there is a power of 2. Okay, so this is minus m is equal to 1, right? So this is minus 1 raised to 1 times 2m factorial over m factorial square 2 raised to 2m, and you set m equal to 1. That's one place where t square comes in, and there is another place when m is equal to square. This will be equal to 2x the whole square times 2m factorial over. Is that clear how I'm picking out those terms? I'm expanding this and collecting where t square is. Okay, so one is when 2tx minus t square raised to 1 plus, and the coefficients here, plus 2tx minus t square raised to 2. One of them is minus t square, and the other one is 4t square x squared. So that's one from this one. And I'm interested in the coefficients. Is that clear? Hopefully, yeah. But we will do this more formally, correctly. So that's, I'm showing how tedious it is. If you really, if I were to tell you to collect all the t raised to 7 terms, you will have to really analyze where are these terms coming in, and it gets tedious very quickly. But we will do manipulate it using sums, and that's the technique we want to learn. So that's equal to m is equal to 1. Let's see. So this is minus, and m equal to 1. This is 2 factorial. M equal to 1, so that's 2 raised to 2. So that's 2 raised minus 2 raised, or minus 2 over 4 plus the 4x squared m is equal to 2 4 factorial divided by 2 factorial square, that's 4, 2 raised to 4, so that's 16. That's equal to 4 cancels out. So 3 over 8. Over 2, right?
3 over 8 over there, and then we cancel the another 4, that goes 3 by 2.
3 by 2, right?
Mm-hmm.
Not 3 by 8, right?
Are you canceling the 4 in front of the x squared?
Yeah.
I didn't cancel that.
Yeah. So if I get rid of this, then 4 factorial by 16, 4 into 6, right? Yeah. So this is equal to 3 by 2 x squared minus half. Often we write it as so p 0x is equal to x, p1 of x is no.
No.
Not a good day. So it is x, p2 of x is 3/2 x squared minus half. Notice how it is going. The L power will start from L, so that's why these are called polynomials. They have finite x and they don't go all the way to infinity. It's also good to point out, often you write in terms of the polar angle. This is cosine theta is equal to 1 because usually you're working in spherical polar coordinates. So this is P1 cosine theta is equal to cosine theta, P2 of cosine theta. And again, to connect it with physics, what is multipole expansion? Multipole expansion, no?
Then you have like you can have like a dipole, quadrupole.
Yes, exactly. So any charge distribution can be expanded as a series of charge alone, a dipole, a quadrupole, and you say it is a 2L pole. And this is exactly those. This is a charge. This is a dipole. Electric potential due to a dipole will have a cosine theta in it. This is a quadrupole and so on. It will get better when we do really spherical coordinates are brought in. Currently, there is only one coordinate. This is theta. And when I bring in the phi also, then that will become very clear. I think in your homework, one of the problem is discussing this, where I do a 2L pole, where that is exactly the multipole is what is being discussed. These plots are also good to have in mind. So if I have x going, so this is x going from -1 to +1. And the maximum value this takes is 1, so P0 is 1, right? So this is P0. So that's a constant. P1 is x, so it starts from -1 +1. So this is P1 of x. This is 3/2 x squared plus minus half. When x is equal to 0, this is minus half, so this is -1, that's +1. So this is minus half, right from here. And when x is equal to 1, 3/2 minus half is equal to 1. So it's a parabola goes like this. And you can do higher order, Legendre polynomials of higher order. I think this is there in your homework also. A quiz, find out a quiz. Plot PQA. Just have a plot to get the expression for that. You can use a handbook to get the P2X and plot it. And so they will all be in that box all the time. But again, hopefully I conveyed to you, it is a little tedious to calculate even PQ. There will be 3 places it will show up. Yes.
The quiz, do you mean P2 of X or P3X?
Oh, P3. Yeah. Should have asked in this plot. No. Thank you. P3fx will start from cube, and then you know that it will have 3 places. So any cubic function will cut the x-axis 3 times unless it has complex roots. Otherwise, it will have 3 roots in there. So let's go back to this expression and process this. And we would like to identify PLX in general. We would like to get a
concrete expression for PLFX, and it is easy, but we'll have to manipulate a little bit. Exactly like these manipulations, summations and doing a sum and undoing a sum. That is what we want to do. So let's go back to this expression. And again, as a user, why is this useful? What is the motivation behind this? Whenever we have translational symmetry, we use Fourier transform. Whenever we have spherical symmetry, we use Legendre polynomials, and an extension of that for the whole sphere is what is called spherical harmonics. So this is the building block of a spherical harmonic. Currently, we are having only one angle, theta. That's like the latitude that we have. Carbondale is on 38 degrees from the equator. So currently, we are only talking about that latitude. You bring in the longitude also, then it becomes spherical harmonics. But latitude is the harder part. The Legendre polynomial is the harder part. The longitude is easy. It is just exponentials. They're basically Fourier transforms. So they are easy. So latitude is the harder part. So this is the main building block of a spherical geometry. Okay. So we clearly see that this has an expansion. Imagine there is a power of 5. There is a binomial expansion in there. So let's expand that out, and we know how a plus b. So again, x and y, right? Let's say a plus b. A plus b raised to m. What is the expansion associated with this? So this will go from, let's say, expand it in n equal to 0 to m, right? There is a maximum power in there. So this is equal to a raised to m times b raised to, no, not m, right? So m minus n and b raised to n. And then you do m factorial right? That's a binomial expansion. So check it for q. So when n is equal to 0, so that's q1, and the opposite will be, I think that's correct. Use that in there, and I have gt comma x is equal m equal to 0, infinity, and write this in R. Raised to m, and do the summation now, where n goes from 0 to m. A is 2t raised to x. M minus m. E is minus, or minus t squared raised to, and I suppose things. No, that's not what I wanted. That's because then x gets the power of negative, right? I don't like that. And this is t raised to m and t raised to 2n. Let's flip this, right? I can treat this as minus 1 raised to m. And this is t squared minus 2px raised to m. That's another thing I can do. So let's discuss that. This remains the same, and this would be this 1 is to m. Here this is t squared raised to m minus n 2 times think so. Put them all together, hopefully this will work. This is m equal to 0 to infinity, and the other sum run from n equal to 0 and 2m factorial. One of the m's cancel out. M factorial, n factorial, and n minus n factorial. M factorial, n factorial, and minus 1 raised to m plus n divided by q raised to m. Q raised to 2m minus 2n plus n and x raised to n. That's not what I want. Help me, I think I'm making a mistake. Okay, I want to go back to this expression.
There was a minus 1 raised to m, like in the original expression and the one we took out common. When
Here?
flipped, yeah. There's a minus 1 raised to m.
This is correct, right?
Yeah, I think so.
Oh, you're saying I missed that there. Oh, yes, yes. So when I wrote it down there, I'm missing that. Okay, yes, okay, so. Okay, thank you. So let's see. So let me write the correct expression first. I think this is right. Okay, start. Oh, already lost so much time. Okay. Let's try this. And you're saying this is minus 1 raised to m, right? Correct. Right. Okay. I do use this, and yeah, maybe that was yeah, that was also, but that was only one of the features I was struggling with. Okay. Do this again. I'm introducing this in there. So there are two sums, m equal to 0 to infinity, n equal to 0 to n, and I'll collect 2m factorial first. Factorial square 2 raised to 2m, that's this. This one in here, a raised to all these, so this is n factorial, m minus factorial, and not to miss the minus 1 raised to m. And I have a raised to m minus n, so it's 2tx raised to minus n, and minus t squared raised to n. But so that's explicitly I wrote that. And now let's collect them together. Equal to 0
infinity. M to M factorial. M factorial, there is one of them cancel out, n factorial and minus n factorial. There is a minus 1 raised to m plus 1 divided by q raised to m. I think I collected all of them. And what is remaining now is t raised to. Oh, that is a 2 raised to m minus n also, right? So 2 raised to m minus n, so which can be written as minus of m minus n. That is a 2 raised to m minus. So 2m minus n plus n, that is 2 raised to m plus n. What else is remaining? So this is t raised to m minus n raised to plus 2n. That's m plus n. And this is x raised to m minus n. Yeah, I think that's what I wanted. So this is, or that's what I was hoping. So this is m plus n. So that was the power I was looking for. Earlier, I think I got confused. Better? Okay. Once more, just to collect all these things together, I'm just copying this down again. You don't have to. I don't want to erase things on the. This is 2 factorial. Minus 1 raised to m plus 2 raised to, this is 2m minus n m, so it's plus. So t raised to m plus n and x raised to m minus n. So pretty much, notice the structure m plus n and m minus n. That's the key piece when you want to look for it. And when you're looking the sum here, this is not a convenient sum. For the second sum depends on the first one, right? So that is a, for every m, you go from n equal to 0 to m. So let's see what is happening in here. So this is your m runs from m equal to 0. This is 0, 1, 2, 3, and so on. Actually, let me run the m on the top. So m is equal to 0. That's m. So this is 0. This is 1. That's 2, 3, and so on. And when m is, if I start from n now, I have to go from 0 to m. Next one would be 0 to 1. Next one would be, this is n. So I do not write this down. So when n is equal, for m is equal to 0, n goes only first one. When m is equal to 1, n goes from 0 and 1. So this is 1, this is 2. When m is equal to 2, it is n goes from 0, 1, and 2, and so on. Is that clear what I mean? The next one will run L5. This sum basically is going over all the dots that I'm showing there. So this is for m equal to 0. So this is m equal to 0, n is equal to 0. This one will be m equal to 1, n is equal to 0, m equal to 1, n equal to 1, and so on. But I would like to change that summation whenever you're adding. Either I can do this addition, or I can start doing an addition in a different form, and that's what I want to. So that's one addition. And now what I'm going to do is that instead of adding on horizontal lines, I will do the addition along this one. How do I know what are those lines? So I will do, this is what is equal in here. M is equal to n plus whatever this line is, this is the slope of that line. Okay, so this is the slope, let us call that 2 times s. So this is 2s is equal to 0, 2s equal to 1, 2s equal to 2, and so on. Right, that's the slope of that line, so that is your 2s. The slope of these lines is m is equal to minus n. Let's call that plus L. So that will be your L order that you're coming up with. So this will be L equal to 0, L equal to 1, L equal to 2, and so on. Right, that's your two pieces that are coming up. And now, what is m plus n? You just add them together. M plus n is equal to L plus 2s. And what is m minus? Did I do this first? No. I want m, right? So if I add them, so it is 2 times m is equal to L plus 2s, and 2 times n, right? Add them, so that is 2 times n.
0 equals 2 and. We are trying that out. Maybe put the ends in the ends and have to that way.
Did I do
L
this?
plus 2L, L minus 2L, 2L is 0. M becomes 0 and that is 2n. So at that time, L become negative, but we see if we change.
M minus n is equal to 2s, m plus n is equal to L. If I, so I have to subtract, correct? Yeah.
Yeah, 2n is L minus 2s.
Yes. So 2m is L plus 2s. 2n is L minus 2s. Thank you. Okay. And what are the variations that is happening? If I want to sum over all, this whole triangle has to be added up. So I have to go all the way from L, going from 0, 1, 2 to infinity. So that's on here. And S now has a limit, right? Whenever I'm summing over S, there is a limit on L. That is the limit that you were seeing in here, but now I have to write it in terms of L. So I'll write that in a minute. But now we can write this as, change all the variables. This is L equal to 0 to infinity. And I have to do the summation over S. I will provide that sum over S in a minute. That will depend on L being even or odd. That's why I'm not writing it. So that is basically the limit. How far does this go? When L is equal to 0, this is only this that is counted. When L is equal to 1, it is just this. L equal to 2, we have 2 of them. Right. When L is equal to 3, that's these 2. And so on. We have to keep doing that, but I have to find a pattern in there that I'll come back. But let's first manipulate the rest. What is m? 2m is L plus 2s factorial. So this is L plus 2s factorial. M is L over 2 plus s factorial. L over 2 minus s factorial, and m minus n is 2s factorial. This is minus 1 raised to m plus n was L. And this is 2 raised to L. That's e raised to L. And x raised to m minus n is 2s. All this to get the power of L straightforward. So what was the guiding principle? Get the power of T in the correct order. Pull out the T, I can actually get, if I compare this with PL, I immediately get the definition of PL, except that I have to get the S here, right? So PL then is equal to PL of X. I get at least a formal expression here is minus 1 raised to L. Whatever depends only on S and not S, I can pull out, so that's 2 raised to L. And summation over S, which we have to figure out, plus 2S factorial divided by and I think I pulled this out, and that is x raised to s. When s is when L is even, so when L is even, S runs from, it is S is in here, or 2S, let's say 2S runs from 0 to 0 itself, it is L, right? So it runs from 1, this will be 2. Oh, so this is so L was even, right? So this is 0. And the next one will be L equal to 2, so S equal to 1 and 3. So this runs from 1, 0. So this is 0, 2, 4, and so on. And it goes all the way till L. And if L was equal to R, how am I deciphering this? Notice this is L equal to 2. I'm starting from S equal to 0 and immediately jumping to 2. I'm not going for 1. So that's the 0, 2 coming in. And it is going in even quantities. And for odd, it is starting from 1. And here it is 1 and 3. And again, it will go all the way to L. So that's the pattern we have. So S in that case, what is the run it is making? L is equal to even. S would go from 0, 1, 2, and go all the way to L over Q. And when L is equal to odd, I can say S would be equal to 1 by 2, 3 by 2, and so on until L over Q. So that we have to explicitly write, but that is now we are going to see that it is really not necessary to do that. So that will be the trick we will see. It seems like this is a ugly form of writing, or at least not a convenient form to write. But let's do one more. So this is what is called Rodriguez formula. So let's I have 10 minutes. So let's look at an identity. Let's consider x raised to 2s is equal to, so this is x raised to 2s in here. That's equal to d by dx raised to L of x raised to L plus 2s, right? Except that there are some coefficients that are missing. So there is, every time you take a derivative, it reduces its power by 1. So if I take L derivatives, it will reduce this power by from x L plus 2s to 2s. But what is the coefficients I'm missing? It will be, the first coefficient will be L plus 2s factorial. So I have to divide that out. Right? So do an L plus 2s factorial. And provide the rest, right? And do S factorial. Let's check this, for example, cube, right? So for 4, let's say S equal to 2, so this will be 4 factorial divided by, let's also say L equal to 1 or 3, let's say. So this will be 3 plus 2, 5 factorial times x raised to 4 will be equal to d by dx of 3 times x raised to 7. Is that correct? Let's quickly do this. So this is 7 times 6 times 5 times x raised to 4. And is that correct? Oh, did I write it in the opposite way? So this should be in the top, right? L plus us factorial over 2s. Let's try that again. So this will be 5 factorial.
5 factorial or 4 factorial?
Oh, 7, right? S equal to 2, 4, 7 factorial over 4 factorial, which is exactly 7, 6. Oh, fine, my bad. Okay, so that's what this identity is. Let's put that in there. So this is equal to minus 1 raised to L over 2 raised to L. And I have to do the opposite, so it is 2s factorial and L plus 2s factorial. Oh, but it already is there, right? L plus 2s factorial divided by 2s factorial of x raised to 2s is d by dx of raised to L. Since it is an L, it can come out of this in summation over s. So this is s starts from 0 or 1 according to this sum in here, and what is remaining is 1 over and x raised to L plus 2s. And this is a complete sum. So now let's understand what this is equal to. I think I can space here. Lost 5 minutes. So let's try to look at this summation. Yeah, how to answer, how to tell this again. D by dx raised to L. S goes from wherever to, it seems like it is going till L, but let's cut this and make it go all the way to 2L. So it seems like we are overdoing it, but let's do what this might be. L plus 2s over L by 2 plus s factorial and L by 2 minus s factorial. So the highest power you begin with is x raised to L in here. And if I were to take L derivatives, how much is left is 2s. So notice s goes from 0 to L, or somewhere in between here, the maximum it goes is L. If I were to write instead 2L, you would think that I'm adding terms. But I'm not really adding terms, because when I take the derivative with respect to L, all those goes to 0. The higher powers do not contribute anyway. So this increase does not contribute. Does not contribute. Because derivatives go to zero. So, like after you take the derivative, they do not contribute. So that's one key factor that it is now 0 to 2L. And if it is 0 to 2L, what is this equal to? So let's say S is equal to 0 to 2L of x raised to L plus 2S and divided by L by 2 plus S factorial. And this is a binomial expansion then. So this becomes exactly equal to x squared minus 1. So let me see if I can motivate this in a second. So this is raised to L divided by 2 raised to 2L. No, L factorial. Because there is in the binomial there is an up term, right? An addition of these terms. So this is L factorial. So, and that be motivated in a minute. I have 1 minute. Yeah, I think I can do this. So I take out x raised to 2L, which can come out. So this is equal to S is equal to 0 to 2L. This then goes from x raised to, I've taken a 2L out. Taken a 2L out, so I have to subtract, right? So it is 2S. Yeah. Okay, I'm not seeing this. Okay, I'll cover this next time. How about that? Okay. So sorry, yeah, today was a mess. Yeah.
You remember summation is when the upper summation is equal to
S equal to 0 to 2L. So what I did was that
no, I got it, but there is S minus the upper summation.
here.
No, the upper
Before that, here.
the summation.
Oh, no, yes, goes to 0 to.
Oh, here I meant S equal to 0 to. Yeah. So 0 to L. It was going from 0 to L. I changed it from 0 to 2L, and my argument was that higher terms do not contribute. That's because of the derivative. But then this is a complete sum. I'm not seeing that.
So we add -1 to the power m at the generating function. We miss that one. Shouldn't this effect on power of t1 like then it become -x?
Say that again?
We miss that -1 to the power m generating function.
Yes.
Yeah. So shouldn't that effect of power of t1 we measure that last
I thought I took care of that
okay.
because there was a -1 raised to n here, and there was a -1 raised to n that was coming up. Check on that. I think I took care of that. The sign was coming correct here, right? This is correct sign from my understanding. Okay. But I'll do this. I'll clarify this so that there is no confusion. One shouldn't have this confusion. But all these small things, that's what I can ask in an exam. So you asked, these are all long problems. I won't ask the whole thing, but I can ask you from here to there, right? From this to this. That all of us will agree is something that can be done in 10 or 15 minutes, kind of little level. Does that help? Yeah. Sorry. Yeah. Okay. Bad day. Okay. Thank you.